There's a skull in a museum drawer with a complete set of adult teeth, and every single one is worn flat. No cusps, no ridges, just smooth ovals of exposed dentine. The person died around 30. And that's not damage, and it isn't disease. Across most of the human past, that is simply what a 30-year-old's mouth looked like. Which leaves a question that turns out to be surprisingly hard to answer. What were they eating that did that? And how many hours a day were they doing it? Enamel is the hardest tissue your body makes. It also never grows back. Every mouthful takes a sliver off, and nothing puts it back. So a tooth is a ledger you cannot edit. Anthropologists score that ledger. The system most used comes from Stephen Molnar, published in 1971, running from fresh, sharp cusps up through 8 stages to a flat plate of dentine. In a lot of prehistoric populations, adults are hitting the top of that scale in their 30s and 40s. Not the odd, unlucky person, the normal, expected pattern. Once the enamel is gone, the softer dentine underneath wears faster, so the tooth hollows into a shallow bowl. The body answers by laying down new dentine from inside to keep the nerve sealed. Usually it wins that race, sometimes it doesn't. Then you get an exposed pulp, an infection, and an abscess that eats a drainage hole straight through the jawbone. You can see those holes. The front teeth carry marks too. Fine scratches on the lip side, running at an angle, left by someone gripping hide in their teeth and cutting upward with a stone blade. So the mouth was a workshop as well as a stomach entrance. But holding hide doesn't flatten molars. Something in the food itself was doing the sanding. For that, go to Abu Hureyra, on the Euphrates in northern Syria. A settlement occupied straight through the shift from foraging to farming, dug in the 1970s ahead of a dam that now covers it. The human remains were studied by Theya Molleson, who wrote about them for Scientific American in 1994. What she found first wasn't teeth. It was toes, knees, and backs. Deformed toe joints, arthritic knees, lower vertebrae under heavy strain, all in a pattern that matches kneeling, curling the toes under, and rocking forward and back for hours. What she was rocking over was a saddle quern, a slab of stone, a smaller stone in both hands, and grain crushed between them. Then, in the same skeletons, badly worn teeth. Here's the part that reframes everything. Those querns were sandstone and basalt. Every stroke sheds a little stone dust into the flour. You are not just grinding your food. You are eating the grindstone. That's the reading I find most convincing. The main abrasive was rarely the food. It was the equipment and the environment, ground finer than anyone could see or spit out. And it wasn't only querns. Wind-blown sand settling on drying meat, ash from cooking directly in embers, sand inside shellfish on a coastal site, which is why shell-midden people have famously wrecked teeth. Plants fight back too. Grasses grow tiny silica bodies called phytoliths in their leaves, hard enough to scratch enamel. Chewing wild grass stems is, at a microscopic level, chewing glass. So grit explains how sharply the teeth wore. It doesn't explain the other half of the picture, which is how long the average mouth was working every single day. For scale, look sideways at chimpanzees. On a raw, fibrous, low-calorie diet, they spend somewhere between 4 and 7 hours a day chewing. Chewing is most of what a chimp does. A modern human, on modern food, chews for roughly half an hour a day. Somewhere between those two numbers is everyone who ever lived before agriculture. Nobody held a stopwatch to a Paleolithic meal, but you can approximate it in a lab. In 2016, Catherine Zink and Daniel Lieberman published a study in Nature where volunteers ate raw goat meat and raw tubers while electrodes measured their jaw muscles. Raw meat turned out to be almost impossible. People chewed 40 times and still had a lump of tissue they couldn't swallow. Human teeth are hopeless at shearing raw muscle fiber. Then they sliced the meat with a stone flake and pounded the tubers. The estimate that came out was around 2 million fewer chews a year, and roughly a sixth less force in every bite. 2 million chews. From slicing. That's what simple processing buys you. and it tells you what the number looked like before anybody thought of it. You can see the consequence on the bone. The temporalis muscle fans up the side of the skull. The masseter runs from cheekbone to jaw, and both leave ridges and scars where they anchored. On older human skulls, those anchor points are broad and deep, the jaws thick, the dental arcade wide. Chewing muscles conditioned the way a distance runner's calves are conditioned. By use, daily, for life. So, gritty, tough, and constant. That's the mechanics. What we're far less sure about is the actual menu. What was in the mouth doing all that work? There are two main ways in. The first is isotopes. Carbon and nitrogen locked into bone collagen record roughly where in the food chain someone sat, and broadly what kind of plants fed them. Some Neanderthal bones come back with nitrogen values as high as hyenas, which has been read as an overwhelmingly meat-heavy diet. That reading is genuinely contested, and specialists still argue about what those values mean. The second way in is dental calculus. Hardened plaque, which nobody brushed off, and which traps microscopic starch grains and plant fragments, and then fossilizes them against the tooth. In 2011, Amanda Henry and colleagues published starch grains recovered from Neanderthal calculus from Shanidar in Iraq and Spy in Belgium. Date palm, grass seeds, and grains showing damage consistent with cooking. Then it gets contested. At El Cidrón in Spain, Karen Hardy's team reported chamomile and yarrow in the calculus. Both bitter, both nearly calorie-free. She suggested deliberate self-medication. Others countered that those plants could have arrived in the stomach contents of a herbivore that was eaten. That disagreement is not settled. I lean toward caution, because two plants is a very thin thread. And here's the honest limit. Isotopes average years and mostly track protein. Calculus catches only what happened to stick to a tooth. Both are samples of the durable and the lucky. Soup leaves nothing. Boiled greens leave nothing. Honey, eggs, insects, marrow, fruit eaten in 5 minutes under a tree, all invisible. We do not know what most prehistoric meals were, and we will never taste one. There is no record of flavor. What we can say is narrow but solid. It was chewy, it was gritty, and it took a long time. Then, quietly, it stopped. The first thing that changed was fire. At Wonderwork Cave in South Africa, Francesco Berna's team reported burnt bone and plant ash from deposits about 1 million years old, deep inside the cave. At Gesher Benot Yaakov in Israel, excavated by Natma Goran Inbar, there are repeated hearth areas with burnt seeds, wood, and fish, dated to around 780,000 years ago. Cooking softens starch and unwinds protein. Richard Wrangham's argument, laid out in Catching Fire in 2009, is that this is the moment human food got cheap to chew, and our bodies rearranged around it. The second thing was grinding. At Ohallo II, a waterlogged camp by the Sea of Galilee, a grinding slab, about 23,000 years old, still carried wild barley starch on its surface. At Bilancino in Italy, a team led by Anna Revedin reported flour made from bulrush roots on a stone around 30,000 years old. Flour, thousands of years before anyone planted anything. But grinding was a trade, not a win. It cut your chewing time and raised your calories. It also poured stone dust into everything you ate. Easier meals, faster teeth. That trade only ended recently. Finer sieving, better querns, boiling in pots, and finally steel roller mills in the 1800s. Within a few generations, grit essentially disappeared from bread. You can see it in the skeletons. Heavy flatware falls away, and cavities climb because soft, sweet food sits on teeth that no longer sand themselves clean. A different mouth, with different problems. Daniel Lieberman has argued, in The Story of the Human Body in 2013, that jaws which never work hard in childhood grow smaller, leaving teeth crowded and wisdom teeth with nowhere to go. That idea is debated. Genetics matters, and orthodontists disagree about how much chewing load really shapes a growing face. If your own teeth worry you, that's a conversation for a dentist, not a video. But the shape of the story holds. Your molars were built for a job that no longer exists, and most of them will outlive you with their cusps still sharp. Next time you eat something that takes real work, a hard crust, a tough piece of meat, notice how long your jaw stays busy. That's about 10 seconds of an ordinary Stone Age lunch.